With simplicity, speed, and reliable navigation, Desert Wave and our AUV Phoenix placed 3rd overall in the 2019 RoboSub competition. Despite our success, there were many areas in which we wanted to improve. For example, we had to add around 20 pounds of deadweight to make our AUV less buoyant, causing us to earn a point penalty.
Phoenix can only locate different challenges by using survey techniques and dead reckoning. Our ability to complete manipulation tasks was extremely limited. We also didn't finish developing our vision software, so we recorded our runs to assist us with developing vision for the next competition. A year passed and we created a new game plan by designing a new AUV that builds upon our previous successes and addresses our previous weaknesses. This video documents the process we have made towards completing our new AUV, Dragon. Once completed, Dragon is designed to compete alongside Phoenix, directly addressing her weaknesses. With 2 AUVs, we believe we can win the RoboSub competition. Here is a diagram of the software and hardware architecture of Phoenix. Phoenix has one Jetson computer and a Teensy controller to interface with the actuators and sensors. Dragon uses a similar design, except that the role that the Teensy controller plays is divided up into 4 different student design boards to improve sensor handling and performance.
Instead of 3 holes, Dragon has 5 smaller ones. Separating the components into 5 holes allows for members to work in parallel without relocating the entire AUV. Due to recent health events, this design decision has proven to be incredibly useful. This design also reduces the need for dead weight by reducing the overall water displacement. Each hole is tested for leaks before being assembled to the rest of the AUV. The thruster hole houses all of the electronics to operate Dragon's 10 thrusters. Inside the holes are student-designed printed circuit boards. Power to Dragon's thruster power bus can be controlled by an on-off switch. In case of an emergency, a connector can be easily removed that will kill power to the thruster power bus, acting as our kill switch.
Our previous AUV was not capable of earning points in challenges that required marker droppers, torpedoes, and advanced object manipulation. With our pneumatic system, that will change. Our marker dropper, torpedo launcher, and grabber arm were all designed with reliability in mind. Our pneumatic grabber was inspired by a design from Team Bumblebee. Here's some footage of us measuring its grip strength and then picking up blocks. While still under development, it is showing a lot of promise. Each of these components utilize pneumatic cylinders operated by solenoids that are controlled by our custom pneumatics board. Before completing assembly of the pneumatics hull, a program was designed to test fire each solenoid one by one.
Our marker dropper has been tested dozens of times without fail. Our torpedo launcher uses a pneumatic cylinder to open a hatch in order to release a spring-powered torpedo. It was first tested on land and then in water. We adjusted the density of the torpedo to achieve the right buoyancy to make it fire straight consistently. Dragon has a Jetson computer and 4 separate student-designed boards. The main board controls the motor, pneumatic, and sensor fusion boards. The main board sends the current control mode to the motor board, and its LEDs will mimic the mode that is defined on the main board. The mimic and LED color and pattern indicates information is received.
Navigation to the challenges is accomplished in 2 steps. Mid-course guidance achieved through surveying and dead reckoning with the aid of sensors like the DVL and fiber optic gyro. The sensor data is fused in Dragon's sensor fusion board and then relayed to the main board. Terminal guidance is achieved by means of visual servoing using one of 2 onboard cameras.
During the competition, Phoenix and Dragon will both choose a different side, bootlegger or G-Man, and pass through the gate. Phoenix will attempt the Make the Grade challenge by hitting the correct buoy and then surface in the octagon. Dragon will attempt to move the bottles to the appropriate table in the Cash or Smash challenge, open the bin and drop her marker droppers into the collecting challenges and fire her torpedoes into the smaller hole of the Survive the Shootout challenge. Finally, if Phoenix was not successful in either surfacing the octagon or touching the correct side of the buoy, Dragon will attempt those challenges. If Phoenix was successful, the team will call the end of the run after Dragon completes the torpedo challenge.
We use a subsonus passive sonar to find acoustic signals underwater. We tuned its parameters at the Transdeck facility to get accurate pinger headings. We have all of next year's target images printed and ready to go for in-water testing when it is safe to do so once again. In the meantime, we are hard at work developing algorithms to identify them. For identifying competition elements, like the path markers, Dragon will use a hue saturation value filter technique. For identifying more complicated images, like the G-Man or Bootlegger, the team is training a neural network.
This simulator works as a testbed for most of the AUV's vision development. One module of the interface reports telemetry data from the AUV, while another module is used to set the operation mode. Last year, we used the simulation environment to test Phoenix's capability to navigate to a specific location taken in by user input. The simulator was modified this year to tell the programmer if the AUV is able to see an object in the simulation environment. This is useful for when we are in the water because our AUVs will be able to identify if it is within a range of its target and with what offset from center in a northeast down direction it is within that range. Still under development is a feature that will allow the simulation AUV to correct its position to the target once within its range and identifies the object with vision training. When we're not able to test in the water, we have a simulator with a 6 degree of freedom physics model of the AUV that simulates the movement of the robot in response to motor value and generates simulated sensor readings. Additionally, the team utilizes a software-in-the-loop simulator to allow the AUV code to be tested within a modeling environment. This enables remote testing of software without requiring the AUV hardware by simulating the serial Teensy Jetson connection over a user datagram protocol interface.
Due to our university labs closing, one of our mentors graciously opened his garage as Le Javardi Labs, allowing us to continue our work. Members are required to wear masks and schedule a time to attend an individual work session. The garage is equipped with hand sanitizer and Clorox wipes, and all equipment is cleaned before and after a student worked there. Due to the modularity of the Dragon's design, team members are able to easily take home various components of the AUV to conduct work sessions in their own homes.
Even though we're primarily working from home, that hasn't stopped us from recruiting new team members. For all other tasks that didn't require meeting in person, our team turned to using Zoom and Slack to collaborate and keep each other updated on our progress. Dragon remains to be a work in progress. Currently, we still have to finish designing, building, and assembling the computer hull. Once complete, we can finish designing Dragon's frame and begin her final overall assembly. There's also a significant amount of work left in software development and testing, which we hope to prioritize this year once the construction of Dragon is complete. While progress has been slower since we are no longer able to meet as a team, slowly but surely, we believe that the ripples of our hard work will bring a wave of success.